Welcome, PCS members and friends, to our PCS IBS seminar. Today, we have a pleasure of hosting Dr. Glenn Wagner from Zurich University in Switzerland. And our scientific host today is Zoom, and I will ask Zoom to introduce our speaker.
Hi, Glenn. We're very happy to have Dr. Glenn Wagner today to give us an exciting talk about superconductivity in bilayer graphene. Glenn is a brilliant researcher. He finished his PhD at University of Oxford under Professor Steve Simon. Glenn worked on many topics at Oxford, including transport in many in the multilayer graphene, fractional quantum Hall, and also bilayer quantum Hall. And after his PhD in 2021, he moved to University of Zurich, worked with Professor Titus on more exciting subjects like higher order topology, unconventional superconductivity, and also many important work on twisted bilayer graphene with many exotic phase that discovered recently in experiment. And now let's welcome Glenn.
Thanks for the introduction, Zung. So as Zung said, I'm going to be talking to you about superconductivity in Bernal bilayer graphene. So this is something that was discovered experimentally only about 2 years ago, so it's fairly recent results. And I'm going to present some theoretical framework to try and understand these experiments. So I would like to thank my collaborators to start off. So this is some work that I did with my PhD advisor from Oxford, Steve Simon, and some other people both in Oxford and Princeton and Ghent. And so let me just quickly give you the outline, what I'm going to be talking about today. So I want to start by putting this work a little bit in a broader context of flat band systems, such as twisted bilayer graphene, which you might have already heard about. And I'm going to present to you the experiments that motivated this work. And after that, I'm going to start discussing the theory in increasing amounts of detail. So I'm going to start with a very simple model, just looking at the Fermi surface of this metal and trying to understand what we can say about superconductivity just by looking at the Fermi surface. Then I'm going to start using slightly more sophisticated tools, including the random phase approximation, and finally, the functional renormalization group. So we'll sort of start off in a fairly intuitive way and then get increasingly more detailed. So before I talk about the actual material that is going to be the focus of this talk, this Bernal bilayer graphene, I want to just say a few words about twisted bilayer graphene, because of course this attracted a lot of attention in the last 4 or 5 years. And it's actually what motivated these experiments on Bernal bilayers. And so what happens in twisted bilayer graphene is you take 2 layers of graphene, which is a honeycomb lattice of carbon atoms. You stack these 2 layers and you twist them. And what you can see on this figure on the left is that the twisting leads to a so-called moire pattern, which is a periodic pattern which has a much larger period than the fundamental lattice scale. So in this moire pattern, you can have up to 10,000 atoms in a single unit cell. And the consequence of having this moire pattern is that it leads to extremely flat bands. So this is illustrated in this figure in the center. You see that when the twist angle is 5 degrees, these bands are fairly dispersive. But when you twist the material to about 1 degree, this is this so-called magic angle, you can see that the bands become completely flat. And these flat bands lead to a high density of states. And this was predicted back in 2011. And in 2018, they actually managed to build this material in experiments. And what they saw was quite surprising. They saw superconductivity. This is shown in this, this phase diagram on the right. They saw superconductivity and some insulating states. So the blue is the superconductor, the red is the insulator.
Sorry, I have a question.
Yes?
So at the magic angle, you have only one band, which is flat. I see it from P equals to 0. Are the other bands flat as well?
Right. So you see in this figure, there's one band that's flat indeed, but it turns out that this band is 8-fold degenerate. So there's really 8 flat bands that are all degenerate. But
do you need more than one band that needs to be flat?
Well, in principle, yeah, you could have pairing within one band. In twisted bilayer graphene, we honestly don't know what the superconducting mechanism is yet, so we don't know what role these bands play. But the important thing seems to be that you have at least one flat band, and this gives you a high density of states, and the high density of states probably leads to some correlation effects that give you superconductivity. But it's impossible to really be more precise because, yeah, as I say, we don't know what the mechanism for superconductivity is here.
So
it could be something
you will just one flat band, is that correct?
Sorry?
You will be okay if there is only one flat band, or in your systems you're looking for more than one?
It's okay if it's in principle if it's one flat band. Although in graphene you usually have 2. Yes.
To make the pairing mechanism, maybe you 2 at least, I think.
Right. So if you want to have your pair to be satisfying like time reversal symmetry, you pair k and minus k, then at least in this case of twisted bilayer graphene, you would need at least 2 bands because each separate band lives in one of these valleys of the graphene, and you need 2 valleys to satisfy time reversal symmetry. Right.
I had another question. If you change the angle back from the magic one to a non-magic one, will the superconducting phase disappear?
Yes, eventually it disappears. It exists only for some small range of angles close to the magic angle.
I have also another question that I'm sure is super well known, but I'm not an expert in flat bands. So these are the kind of flat bands that I learn about compact localized states and so on, or they are different? No, completely different, right? Completely different. Okay.
These bands are, in principle, you can think of them as churn bands. So it's similar to Landau level in the quantum Hall effect. That's the sort of best analogy. So it's the same as when you've got a 2-dimensional metal and you apply a perpendicular magnetic field and you get these Landau levels. These also are flat bands, and it's the same thing here, except there's no magnetic field.
Then I have a follow-up question again. Did you apply magnetic field here, or is Terence probably implies that you have broken something?
Sorry, I didn't quite get that.
The question is whether what's the mechanism of breaking time reversal? You mentioned that there are not many churn numbers.
So you've got a churn number, but you've always got a churn number in one band, and then you've got another band with the opposite churn number. So time reversal is still satisfied in this material. It's just that the churn bands come in pairs. Yeah. But what you can get is you can get spontaneous time reversal symmetry breaking in this material. So even in the absence of a magnetic field, you can get this quantized anomalous Hall effect. So they spontaneously breaks this symmetry due to interactions. Okay, so right, so this is this phase diagram of this material. You see this superconductivity, and in proximity you see some insulating phase. This got people quite interested because it looks a little bit like the phase diagram of the cuprates. And one of the things that that seemed striking is that it's related to this magic angle. And so there were some experimentalists led by Andrea Young's group at UCSB who wanted to prove this, that the magic angle and this twisting is really fundamental to get this superconductivity in graphene-based systems. And so they took some non-twisted system, in this case, rhombohedral trilayer graphene. So you just stack 3 layers of graphene, you don't twist them. And they wanted to do these experiments to show that you don't see superconductivity here, you need the twisting to get superconductivity. But actually the surprising result they found is they did see superconductivity, which they hadn't expected. And so you can see on the left this band structure of the material. So there's 2 bands close to the Fermi energy. And in fact, you see a sequence of bands going from the black to the red band. And this is for different values of this so-called displacement field. So you take these 3 layers and you apply an electric field perpendicular to the layers. You can do that by applying a gate voltage. And you can see that as you increase the gate voltage, as you increase the displacement field, the bands become flatter and flatter. So this is what you see in this figure B. And the phase diagram on the right is showing the resistivity as you tune the density and this displacement field. And you can see that above some critical displacement field, you can see superconductivity. This is in light blue in this diagram. So it seems that as you make the bands flatter and flatter by applying this displacement field, your material eventually becomes superconducting. And the TC is quite a bit lower than in twisted bilayer graphene. In twisted bilayer graphene, it was about 3 Kelvin. Here, the TC is about 1/10 of that. But still, this was an unexpected result and motivated some further studies. Namely, instead of studying 3 layers, you can just study 2 layers of graphene. So those experiments were done next. So now you just...
Could I ask a few questions about the last bands? So there, do you have a level crossing at 0 between 2 bands?
So at 0 displacement field, you have, indeed, you have like a band touching point. But as you apply the displacement field, you open up a gap and yeah, you have a gap in the system.
And so let's say you put the displacement field and then there is a gap, but close to Ka 0 to equal to minus and plus 0.1, the bands are not really flat. I mean, they're really bent.
Yes.
And that does not affect superconductivity at all?
Right. So this is one difference to twisted bilayer graphene. In twisted bilayer graphene, you've got completely flat bands. Here, you've got this flat region close to the K points. And the point is that if you look at the x-axis on this phase diagram, the units of the density are extremely low. These are very low densities where your chemical potential is in this region where the bands are flat. And so you know, for superconductivity, it's the things close to the Fermi energy that are important, and the Fermi energy is in this flat band space. Yeah.
Thank you.
Good. So then the next experiments that were done were on these Bernal bilayers. And once again, they could get superconductivity. Again, you see the band structures becoming gapped and flatter as you increase the displacement field. But the interesting thing here is that they only see superconductivity when they apply a magnetic field, which is somewhat surprising. Usually what happens is you destroy superconductivity by applying a magnetic field. Here, it's the opposite that's happening. And this is something that we're going to try to understand in this talk. And if you look at the Fermi surface, this is in figure D, you see that the Fermi surface goes through some transitions. You start with these 3 disconnected Fermi pockets, then you increase the doping. At some point, these 3 pockets merge, in a Van Hove singularity where the density of states has a peak, and then you end up with an annulus as a Fermi surface, and at some point the annulus merges to a simply connected Fermi surface through a Lifshitz transition. So you've got these sequences of transitions in the Fermi surface, and the superconductivity seems to be associated with the Van Hove singularity, this peak in the density of states. So if you look at the density at which the superconductivity occurs, it's more or less where this peak in the density of states happens, which is not so surprising. We know that high density of states favors higher TC for the superconductor. And here the TC is quite a bit lower. Again, it's about 26 millikelvin in these experiments.
Sorry, some examples that you have shown for this three-layer graphene and the twisted bilayer graphene. May I have some comments about the type of the pairing? The superconductivity you mentioned are simply the S-wave pairing, or you expect to have some more non-trivial pairing?
So I'm going to show some results later that we seem to find P-wave pairing in Bernal bilayer graphene. So I'll explain later how this P-wave superconductor emerges. Yeah. Good. And finally, the next experiments that were done were, instead of applying a magnetic field to get superconductivity, something else you can do is you can add a substrate to this material. In this case, it's WSE2. And the point of this substrate is that it has some heavy elements and strong spin-orbit coupling, whereas we know that the graphene has essentially zero spin-orbit coupling.
Sorry, can I ask?
Yeah.
So in the tri-layer graphene, so in the case before where you have the Van Hove singularity and all this, so
yeah.
Here, right, figure D, right?
Yeah.
So here you have a singularity, and so essentially you are looking at Kx and Ky. Those are those surfaces, like those three pockets that you are looking at, those Fermi pockets.
Mm-hmm. Yeah.
But then when you plot figure B, then you are only plotting it against Kx direction. So
yes.
Presumably you have integrated the Ky direction.
That's
yes?
right. Yeah.
So now my question is, in the earlier plot, in the tri-layer graphene, you didn't have this D figure. So so in this case there is no singularity in that like this.
So actually, yeah. So the figure D here is also showing these contours of the energy, and you can see that it actually has the same sort of three pocket structure. So actually, these materials are fairly similar in the sense that you also see in figure C this peak in the density of states. So those are common features of both. Yeah.
That is again like the same thing as the Van Hove singularity that you were talking about.
Yes. It also has a Van Hove singularity. This material. Yeah. Good. So yes, finally, another way to induce superconductivity, instead of applying a magnetic field, what you can do is you can induce spin-orbit coupling by proximatizing it with this WSE2 layer. And again, you see this plot of the resistivity for different values of the displacement field and density. And you can see that the superconductivity only happens for positive displacement fields. And the reason for that is that for positive displacement fields, you're pushing the electrons, you're applying an electric field, you're pushing the electrons towards the WSE2, you're inducing the spin-orbit coupling. This gives you superconductivity. On the opposite side, when you apply the negative displacement field, the electrons don't feel the WSE2, they don't have the spin-orbit coupling, and so they're not superconducting. So this is a proof that it's really the WSE2 that's inducing the superconductivity. And actually here you can get a TC that's quite a bit higher than before. Actually, it's almost 10 times as high as with a magnetic field. So that's something else that we're going to try and explain with our mechanism. Okay.
Sorry,
yeah.
From the figure, how can I see that? From figure A, how can I see that when you apply the displacement field, electrons are being pushed towards WSE2?
So the displacement field is just an electric field perpendicular to these layers. And for the positive displacement field, the electric field is such that all the electrons get pushed up, whereas for the negative displacement field, all the electrons get pushed down. And in one case, they feel the WSE2, in the other case, they don't feel the WSE2.
Okay.
Yeah. Good. So there's been several works on this subject already, trying to understand what the superconductivity is. The first ones were just looking at phonon-mediated superconductivity, very similar to what you have in conventional superconductors. It's just this standard BCS theory. But one reason to think that it could be something else is that the superconductivity is very close to some electronic phase transitions in the system. So you have different types of magnetic transitions, and the superconductivity is at this magnetic transition. And so this motivated some further work that was looking at this quantum phase transition being relevant for the superconductivity. So you had superconducting pairing coming from these quantum critical modes. And then there was some other work trying to explain why the magnetic field or the spin-orbit coupling is important, which was saying that you've got a strongly fluctuating superconducting order parameter, and by applying a magnetic field, you sort of pin this order parameter and therefore stabilize the superconductor by suppressing the fluctuations. And finally, there was some work that was proposing a purely electronic mechanism. So you completely forget about the phonons, and you only have electron-electron interactions, and you can get pairing from this by a mechanism called Kohn-Luttinger superconductivity. And in fact, this is the mechanism I'm going to be focusing on in today's talk. So just to explain you the basic ideas behind Kohn-Luttinger superconductivity, I'll give you a somewhat intuitive picture for what's going on. So to get superconductivity, you need to get some attractive interaction because you need electrons to pair up into Cooper pairs. And of course, if you only have electron-electron interactions, they're always repulsive because electrons are negatively charged. So you need some way to get some effective attractive interactions between the electrons. And the way you can do that is by screening. So if you're in a metal and you have some charge, then you're going to have some screening of that charge. So you've got a negative charge, you've got a positive charge cloud around that charge. And now imagine you have more positive charge around this negative charge, then at some point it becomes a net positive charge, and this can attract another electron, which is negatively charged. So by over-screening, you can actually generate some positive attraction. And the way we simulate that in our calculations is by doing so-called random phase approximation calculations of the screening. So if V naught is the bare interaction, then this RPA screened interaction has this form here, where pi is the polarization function. And in terms of Feynman diagrams, it's coming from summing up this infinite series of bubble diagrams to renormalize the Coulomb interaction. And this is related to something called Friedel oscillations, which happen in a metal. When you have an impurity in a metal, then the charge around this impurity is not uniform, but it's got this oscillating pattern. And so you can see that at some points in this oscillating pattern, the charge is higher, and in some regions it's lower than average. So you've got these regions where actually the charge is depleted, and again, this can cause some attraction. And usually this happens in some higher angular momentum channel, not in the S-wave channel, but usually P or D-wave channels, because the S-wave channel is purely on-site and attractive, whereas higher angular momentum corresponds to further distances in the pairing, and there it can become attractive. So the Kohn-Luttinger mechanism actually doesn't happen naively in 2 dimensions. And the reason for that is that for parabolic bands, you're susceptibility is constant in 2 dimensions. Hello, are you still there? Hello?
I hear you all the time.
Okay, I don't see the video anymore.
I don't see either. Yeah. Maybe
Okay.
they are working on this. Can you tell me a naive question?
Sure.
You say that you can induce the superconductivity either by magnetic field or by spin-orbit interaction in the substrate.
Yes.
But these two are different. The magnetic field breaks time reversal, symmetry, and spin-orbit does not usually.
Yes. So actually, the way this the spin-orbit coupling works in
Oh, here they are. So maybe you mention it later. Okay.
Yes, I'll come back to that actually, but I'll show that actually the spin-orbit coupling and the B field have more or less the same effect. Exactly.
Okay.
Yeah.
Let's continue.
Okay. I lost you guys for a bit. Are you back?
Can you come
Yes,
back to
we are.
the bubble diagram?
Yes.
Yeah. I have one question here. So in the case that you want to have over screening, is it you need to have a cheap way to create the particular hole pair?
Sorry, I didn't get the last bit.
In order to have the over screening, you need to have a cheap mechanism to create the particle hole pair. Like that's a very easy way to create the particle hole pair.
I still didn't understand the last word.
So you need to have very easy way to create the particle hole pair.
Yeah. Yeah.
So is this the reason that you need to have the lower band in the bilayer graphene? Is this the reason that you need that?
So typically this overscreening is going to be larger when you have a large density of states, right? In the sort of naive, Thomas Fermi picture of screening, this bubble diagram is just the density of states. And so this is why the flat bands and this Van Hoff singularity are important, because the peak in the density of states corresponds to higher screening. That's basically why the superconductivity seems to occur there, because you have high density of states, higher screening. Also, high density of states favors superconductivity via increasing the TC. So you've got these two different effects that both mean that you get a higher TC when the density of states is highest.
I see. Okay, thank you.
May I ask a question also? I didn't get exactly, why do you call it overscreening? Why it's not usual screening? I didn't get it.
You can make the denominator become negative.
Yes.
Right, so the overscreening just means that you've got some attractive interaction in some angular momentum channel. Usually it's not in the S-wave channel, but in the P or D-wave channel, you have a net attractive interaction after the screening. That's what I mean by overscreening.
And also the question is for RPA method correctness, you should rely on high density approximation. Is it true here that there is a high density of electrons?
Right, the density is high. That's right. Yes.
So which one is more important, Van Hoff singularity or the flatness of the band in terms of high density?
Right. So, yeah, I would say that the important thing here is just having a high density of states, which is somewhat related to both, really. I mean, the Van Hoff singularity is in principle, it's just like a single point, and it will get broadened out by various effects. But really, the flatness of the band means that you've got a high density of states over fairly large density region. And yeah, that's what's important, just having this high density of states for the screening. Good. So So next, I said that we can have this Kohn-Luttinger mechanism to explain the superconductivity in Bernal bilayer graphene, but actually there's a problem, because naively, if you just have parabolic bands in 2-dimension, then there's actually no Kohn-Luttinger mechanism. This has been known since the 1990s, and the reason for that is, for parabolic bands in 2D, the polarization function pi is completely flat. It has no momentum dependence, and therefore it doesn't generate any interaction in non-trivial angular momentum channels. So there's no contribution in the P, D, and so on channels. And as I was saying before, it's in these higher angular momentum channels that we expect to get the attractive interaction. So there is a way to get Kohn-Luttinger in 2D for parabolic bands, but it's a higher order effect, and this is expected to be extremely weak. So we need some way to get this to work, and this is where the magnetic field can come in. Because if you apply a magnetic field, you actually have a Zeeman term, which makes the Fermi surface of one spin species larger than the Fermi surface of the other spin species. And in that way, the polarization function is no longer constant for one of the spin species, and this gives you attraction in some non-trivial angular momentum channel. So this is how the magnetic field can actually enhance the superconductivity. And something else is that, of course, our bands are not perfectly parabolic. In fact, there's all this trigonal warping, and you saw that it was 3 different Fermi pockets. So this is another effect that causes the superconductivity. It's the fact that the bands are not parabolic when you apply the displacement field. You saw that without the displacement field, the bands were almost perfectly parabolic, but applying the displacement field changes that. And so that's why the displacement field is also important to get the superconductivity. So we need these 2 different ingredients to get this Kohn-Luttinger mechanism to work. So having given you this broad overview about Kohn-Luttinger superconductivity, let me get into a bit more details about this material, Bernal bilayer graphene. So as mentioned, it's 2 layers of graphene. And so we've got 4 atoms per unit cell. We can write down a simple tight binding Hamiltonian for that. And this gives us the Fermi surfaces that I was showing here. The important thing is that there's this valley quantum number with the K and the K prime valley being related by time reversal. So there's 2 valleys, and there's also 2 spin flavors. So in total, there's 4 degenerate spin flavors, isospins. And there's 2 ways to break this degeneracy. So one is by applying the magnetic field, which has a Zeeman term. And the other one is inducing spin-orbit coupling, which in this language looks like SZ tau Z, where S is the spin Pauli matrix and tau is the valley Pauli matrix. So now you see that actually in this kind of Pauli matrix notation, the magnetic field and the spin-orbit coupling look very similar. And in fact, they're completely equivalent as long as we neglect scattering between the 2 valleys. And because these 2 valleys are far apart in momentum space, the scattering is quite weak. And so to a good approximation, spin-orbit coupling and magnetic field are equivalent. And this is why we have a unified mechanism for superconductivity coming from either magnetic field or spin-orbit coupling. So this is showing the Fermi surfaces again for an applied Zeeman field, just again illustrating the fact that spin-orbit coupling and magnetic field have the same effect. So what I'm plotting here are the 4 Fermi surfaces of the 4 isospins, which are the 2 valleys and the 2 spins. And you see that for the magnetic field B, the Fermi surfaces with the same spin are the same, whereas in the case of spin-orbit coupling lambda, the Fermi surfaces with opposite spins are the same. So you see that basically the difference between spin-orbit coupling and magnetic field is just how we assign labels to these Fermi surfaces. But the actual Fermi surfaces look identical. And the other thing that happens when you apply this magnetic field or spin-orbit coupling is that you split the 2 Van Hove singularities. So one of the spin flavors goes for a Van Hove first, and then the second spin flavor goes through the Van Hove. And in yellow, I'm showing the region where we see superconductivity. So we see superconductivity only close to one of these Van Hove points, and not to the other. So that's something that I will try to explain in our model. Good. So now let me try and come up with a very simple model called the patch model for how you get the superconductivity. So in this figure, I'm showing the Fermi surface again, and you see it's got these 3 different pockets. So I'll call these the 3 patches and build a model schematically shown in this schematic below of 3 patches, 3 lobes. And I've got some interactions between the electrons in these lobes. The U is interactions within a lobe, and the V is interactions between 2 different lobes. And now for superconductivity, I need to solve the gap equation. And the matrix that appears in the gap equation, this matrix M, I can write in this basis of the patches. So, you know, M has got these momentum labels K and K primed, but now I just, you know, pack all the K within one patch into one entry in this matrix. And the diagonals of this matrix are the interactions within a patch, U, and the off-diagonal entries are between the patches, V. And so now I diagonalize this matrix, I find the leading eigenvectors, and you see that there's 2 degenerate eigenvectors with the following phase factors, 1 e to the 2 pi over 3, e to the 4 pi I over 3. And so this eigenvector, if you sort of track it going around the 3 pockets, it picks up a phase winding of 2 pi. And this is exactly what you would expect from a p-wave solution. So these 2 degenerate eigenvectors are essentially the 2 p-wave solutions of this gap equation. And if you look at the corresponding eigenvalue, it's V minus U, and the eigenvalue, if it's positive, will give you a superconducting instability. So it needs to be positive for there to be a solution to this gap equation. And if it is positive, then you've got a TC that's proportional to the exponential of 1 over this eigenvalue. So we need to find a way to make this eigenvalue positive to get superconductivity. That's the important question. So now, naively, we just start off with the Coulomb interactions. The Coulomb interactions are roughly 1 divided by Q, where Q is the momentum transfer. And so the U has 0 momentum transfer. The V has a finite momentum transfer. And so, of course, U will be larger than V because the Coulomb interaction is monotonically decreasing as a function of Q. And so we actually never get a positive eigenvalue. This eigenvalue is always negative. We don't get superconductivity for the bare Coulomb interactions.
Sorry, can I ask a question?
Yeah.
So if you can go back to the gap equation. So did you get this gap equation from a Hamiltonian that you start with? Or how did you get this gap equation? That is my question with this 3 by 3 matrix.
Right. So the way to get this gap equation is, it's very similar to standard BCS theory of superconductivity. You just have some, some Hamiltonian with some interaction term, and you apply mean field theory to this interaction term, solve it self-consistently, and the self-consistency equation is exactly this gap equation here.
Oh, but then you start with an S-wave interaction, or like you start with some assumption there, or because in the very beginning of the talk, you mentioned that the pairing is sort of difficult. So I'm just trying to understand.
So the interaction is just going to come from just the Coulomb interaction of the electrons and plus the screening. And that's what we put into this gap equation, the screened Coulomb interaction. And then we find that it's a p-wave eigenvector that's the leading instability.
I see. So you have a whole like 4 Fermi term and like the full Hamiltonian, and then
exactly.
this gap.
We don't need to make any assumptions about the form of the interaction. We just plug in the full, most general interaction term, and then we solve the gap equation for that.
I see, and you do mean field to obtain this gapping.
Right. You do a mean field decoupling of this 4-point vertex of the interaction. Yeah.
And do you neglect some of these pairings there, or what do you neglect there? Because mean field meaning you are throwing away certain couplings.
Right. So I'll show you later what our prescription is. So we take the Coulomb interaction. We then do this functional renormalization group on the interaction. Then we do mean field decoupling of that functional renormalization group flawed interaction. So it's sort of a two-step procedure. And so the functional renormalization group, this is really taking into account all the quantum fluctuations. This is not a mean field thing. This is really the proper, including all the diagrams. At the end, it's only at the very end, in the last step, when we solve the gap equation, that we then do this mean field decoupling of the interaction.
Okay.
Good. So yeah, so as I was mentioning, if you just put in the Coulomb interactions, U is larger than V, the eigenvalue is always negative, you don't get superconductivity. So this is where the screening now comes in. So as I mentioned before, you do this RPA screening of the Coulomb interaction. You can compute the polarization function via this equation. And at the end of the day, you can generate a positive eigenvalue and hence superconductivity via this screening. So if you look at the formulas here, the V and the U get separately screened. And for V, it's the polarization function at Q that matters. For U, it's the polarization function at 0 that matters. And in figure D on this slide, you can see the polarization function. And you can see that the polarization function is actually peaked at Q equals 0. So pi of 0 is larger than pi of Q. And therefore, U gets screened more than V. And if this effect is strong enough, U gets screened a lot, V doesn't get screened much. And at some point, we get a positive eigenvalue and hence superconductivity. So this is how we get this positive eigenvalue.
I have a question. So when you do the bubble calculation, do you assume that the ground state is superconductor, or you assume the ground state is like a spin liquid at liquid?
So for the polarization calculation, we just take the metallic state, just with the Fermi surface and so on, and then we compute the screening for that. Yeah.
Could it be some subtlety come from that? You are deep in the superconducting phase.
So yeah, this is this random phase approximation that I'm talking about now. But later on, I'll show you results for the functional renormalization group calculation, and there we do this flow as a function of temperature, and for temperatures above TC, there's no superconductivity, so there we don't need to take this into account. And then we stop this flow at TC as soon as we find a superconducting instability. So the functional renormalization group takes into account also the superconducting fluctuations and everything are included in this the screening. So the thing I'll show you later is actually more exact than this thing. Yeah, so that's why you'll see later actually the results from the functional renormalization group are slightly different to these RPA results. But it's just nice to get some intuition from RPA because it's much simpler than FRG.
How much different? Okay,
so mostly the difference is just quantitative. Qualitatively, we see the same physics. It's just the numbers, the TC value is different essentially.
May I ask a follow-up question maybe? Will you show us later a spectrum of this superconductivity phase, superconducting phase? Spectrum of elementary excitations.
The spectrum of the excitations. No, that's not something that I've computed. But I mean, it's a nodal superconductor. We know that it's a p wave superconductor. I'll show you the I'll show you the gap function later. Yeah. So. Right. So then in this phase diagram here, you see this lambda eigenvalue, which tells you TC indirectly. And you can see these two branches coming out from this point where there's the peak in the density of states. And remember that this is what was seen in experiments. They saw also this, this is the experimental result here. They saw the superconductivity following one of the branches, but not the other branch. So now in our case, we see superconductivity in both branches, but it's much stronger in the branch doping towards charge neutrality, which is where they see it superconducting in experiments. And the reason the superconductivity is stronger on this majority branch than on this minority branch is because of these because of the properties of this polarization function. In this figure here, you see the polarization function for these different values of the doping, and you see that doping towards charge neutrality, the polarization function is more sharply peaked at 0, so this overscreening effect is larger. So we can understand this asymmetry in doping towards or away from charge neutrality as a consequence, essentially, of the properties of the polarization function. Indirectly, therefore, the properties of the band structure. Good. And finally, one effect. I was saying that the magnetic field and the spin-orbit coupling are equivalent, but you also maybe remember that I was showing you the experimental results that found a much higher TC for the spin-orbit coupling than for the magnetic field. And the reason for that is that when you have a magnetic field, you have two different effects. Actually, you have the Zeeman term, which is the same as the spin-orbit coupling, but you also have orbital effects. And the orbital effects tend to destroy the superconductor above some critical magnetic field. And so this is why you see that the red curve, as you increase the magnetic field, the TC at some point starts decreasing again because of these orbital effects. Whereas for the spin-orbit coupling, where there are no orbital effects, the TC just keeps increasing continuously as you increase the value of the Zeeman term or the spin-orbit coupling. So this is the only difference between the magnetic field and the spin-orbit coupling.
Sorry, may I ask you a question? The magnetic field, I guess that you apply the magnetic field perpendicular to the seed of the graphene, but if you apply parallel to the graphene, then what do you expect to see?
So actually, this is for an in-plane magnetic field. So for an out-of-plane magnetic field, the orbital effects are much stronger, and you immediately destroy the superconductor. But for the in-plane field, there's still orbital effects, but these orbital effects are quite weak. The reason you have orbital effects is because you still, you can still jump from the top layer to the bottom layer and sort of do like loops like that. So you still have orbital effects. They're quite weak, but they're still strong enough because these energy scales are quite small. These weak orbital effects are still strong enough to destroy the superconductor eventually. So all these experiments are all done in in-plane field. For out-of-plane field, there's no superconductivity seen in experiments.
I see. Thank you.
Good. And finally, just to show you the symmetry of the gap function, you can see two different gap functions that we found in our RPA calculation. We found a P-wave solution and an extended S-wave solution. The extended S-wave solution only occurs very, very close to the Van Hove singularity. The P-wave solution appears in a much broader range of the phase diagram. So it seems to be more stable, this P-wave solution. And I'm going to show you later that in the functional renormalization group, we only see this P-wave solution. So actually, it seems like the P-wave solution is the correct one. And this extended S-wave solution is just the result of some fine-tuning. But we can actually understand where this S-wave solution comes from by, instead of looking at this 3-patch model, looking at a 4-patch model, where we include this central patch as well. And we write down a 4x4 matrix for the gap function now. And this lets us write down this phase diagram you see, where we see that depending on the parameters, you can tune it between a P-wave and an S-wave solution. Okay. So now let me start talking about the functional renormalization group calculation. So the concept of renormalization group is to start off with some theory valid at high energies at some UV scale, and sort of successively integrate out high energy degrees of freedom until you end up with some theory valid at some low energy. And in our case, what we want to do is, we know that superconductivity is a phenomenon at the Fermi surface. So we want to integrate out all the high energy degrees of freedom away from the Fermi surface until we end up with a theory valid at the Fermi surface itself, and there we solve for the superconducting instabilities. So we include all these effects of the things away from the Fermi energy by integrating it out. And the way you do this procedure numerically is by solving this flow equation. So lambda is this cutoff scale, this UV scale. And the interesting quantity we want to study the flow of is the 4-point vertex. It's this Feynman diagram with 4 legs. And you can derive from some path integral formalism how this 4-point vertex changes as you change lambda, as you integrate out these high energy degrees of freedom. And you see that essentially this flow of this 4-point vertex is proportional to some diagrams that are just products of 2 of these 4-point vertices contracted in some appropriate way. So this is the way these FRG equations look. And these are the equations, instead of in diagrammatic form, in sort of the equation form of all the correct indices. It doesn't matter too much how exactly these equations look, but these are just something we can solve on a computer. Yes, was there some question?
Could you go back to the diagrams for a second? So, first of all, is this equation exact? And secondly, what is the small parameter here?
Okay. So you see actually that the first diagram in this expansion is a 6-point vertex, right? And the other one's a product of 4-point vertices. So usually so now this 4-point vertex depends on the 6-point vertex. Then you derive a similar equation for the 6-point vertex, and that depends on the product of 6-point vertices and the 8-point vertex. And so you end up with this coupled set of equations, and it's impossible to solve. It's like a coupled set of equations that never ends. And you have to truncate the series somehow. And we're going to truncate the series at the first lowest order. So I'm going to neglect the 6-point vertex. I'm going to throw away the first term in this expansion, and I'm just going to write the 4-point vertex as a function of the product of the 4-point vertex. So this is the approximation. We throw out this term in this sort of infinite series of equations.
But is it like, do we know that this infinite series actually converges?
I imagine that's extremely difficult to prove for generic interactions. I just know that people have studied these equations for quite some time, since the 1990s, and there's this approximation of neglecting the 6-point vertex. This has been studied and is usually justified.
In your system, is there a way to check whether you can throw away the higher order terms and you are not making a mistake that is important for the experiments, or not?
So yeah, we never included the 6-point vertex in our calculations, but in a way, this is an intermediate coupling approach, I would say. So this will break down if the interactions are too strong at some point. So it's a little bit better than a sort of really weak coupling approach, but it's not completely non-perturbative and so on. So I would call it an intermediate coupling method. And in that sense, the fact that our bands are not completely flat, that there is some dispersion there, the interactions are strong but not super strong, is helping us essentially. So I would be more concerned if you were trying to apply this to, say, twisted bilayer graphene at the magic angle where the bands are extremely flat, because there you don't really have, you integrate out, but there's not much to integrate out because these bands are completely flat. And I mean, you're immediately at the Fermi energy. So I wouldn't really trust this method so much for twisted bilayer graphene. But in Bernal bilayer graphene, the bands are not completely flat, they are dispersive. And the fact that the interaction is intermediate range, I would say is justifying this approach here.
Thank you.
May I also ask a question, please? I wonder, what do you plug here as a bare vertex? What kind of interaction?
So the bare vertex is the Coulomb interaction, the gate-screened Coulomb interaction, with all the form factors coming from the bands. Good. So so these are the equations. Don't worry too much about exactly how the indices are contracted and so on. It's just to show you that in principle this is some set of equations that one can plug on a computer and solve. And I just want to sort of illustrate the usefulness of this method for a different system to start off with before I apply it to our system. So this is some work that was done back about 10 years ago, where they applied this to the Ising-based superconductors. So what you're showing here on these plots is on the x-axis, this cutoff scale, this RG scale, and they take this interaction and decouple it into the different channels corresponding to the different instabilities. You do so via this mean field decoupling of the 4-point vertex. And you can sort it by spin density wave, ferromagnetic instability, charge density wave, and superconductivity. And for the density in figure A, you see that there's first the ferromagnetic instability and then a spin density wave instability. And then you change the density. In figure B, the density is slightly higher. And here you see that first there's this ferromagnetic instability, then there's a spin density wave instability, and finally there's a superconducting instability. And this is where this idea of spin fluctuation mediated superconductivity comes from. The fact that you first have a tendency towards a spin density wave. You first have this spin density wave instability coming in. And then later on at a lower cutoff, you actually have the superconductivity emergence. So it's sort of spin fluctuation induced superconductivity. And of course, at the cutoff scale tending towards infinity, you can't have superconductivity because it's a purely repulsive interaction. So the superconductivity sort of starts off extremely weak, whereas the spin density wave does not. But at some point, the superconductivity overtakes the spin density wave. And this is something similar that was seen in the cuprates, in the high temperature superconductors as well, this sort of spin fluctuation induced superconductivity. So this is a really powerful method, this functional RG, because it takes into account all the different fluctuations and it allows you to study the competition and the interplay between different fluctuations. So we applied this method to our system. Just to give a little bit more specific details, we importantly work with the so-called temperature flow RG. So this cutoff scale we set equal to the temperature, so that flowing this RG is essentially equivalent to going down and down in temperature until at some temperature you end up with an instability, and that's where you have TC.
I have a question.
Yeah.
So in this temperature flow RG, are you using Matsubara green function, or is it use it as use your temperature as the cutoff?
So the way the temperature appears here is inside these polarization functions. You see the pi here has got the Fermi factor in there, and that's where the temperature appears. You just evaluate the polarization function at a given temperature.
Okay, so basically you secretly using the Matsubara in the
yes, exactly. It's the Matsubara frequency when you evaluate the bubble diagram.
Okay, thank you.
Good. And as I mentioned, at each iteration, we compute the superconductivity, and at some point, we find an instability, and that signals TC. Okay, and the next thing is, and this is, you know, a fairly this is sort of for the experts. The way we do this procedure is by dividing the Fermi surface into different patches and computing the 4-point vertex on with different patch momenta as the arguments of the 4-point vertex. So this is the way that these FRG procedures are usually done. So we compute the Fermi surface from the band structure. We compute this sort of tessellation of the Fermi surface, and then we compute the 4-point vertex on these Fermi surface points, and then let the RG flow. And here are some of the results of the FRG. So I've just shown you one of the Fermi surfaces with these 3 pockets, just to sort of illustrate again this 3-patch model that I started with. And the figure in the center shows the 4-point vertex, where one momentum argument lies in one of these patches, and the other momentum argument lies in another one of these patches. In the patches, there's about 60 patches in this calculation. So these are the, you know, X and Y labels are just the patch labels, going from 1 to 60. And the thing you see at 10 to the 6 Kelvin, where we start off our RG flow, you see that the interaction is strongest along the diagonal. This is the sort of red region along the diagonal. And this is exactly what I was showing you in this 3x3 matrix. Basically, you were seeing that the U is on the diagonal, the V is on the off diagonals, and the U is larger than the V, hence the eigenvalue is negative, hence there's no superconductivity. Now we do our FRG procedure, we integrate out things down to 10 Kelvin, look at the 4-point vertex at 10 Kelvin, and now you can see that actually because of the screening, the elements on the diagonal, this U, is much smaller than the V, which is on the off diagonal. So this is exactly this effect that I was talking about, that the screening is stronger for U than for V. And indeed, if we solve the gap equation at some temperature, we indeed eventually find superconducting instability. And this is what I'm showing here. I'm showing the leading eigenvalue as you decrease the temperature, and the divergence of this eigenvalue signals the superconducting instability. And here you see that we find a divergence in this eigenvalue around 10 to the -1 Kelvin, which is roughly the value of the TC that was observed as well. And then the superconducting gap has exactly this P-wave structure that we also found when we did the RPA calculation. In fact, it's a twofold degenerate P-wave solution that we find. And so you can construct these P plus IP superpositions of these gap functions. So in this sense, the FRG is consistent with the RPA in the sense that it predicts the same superconducting instability, the same P-wave solution. But you see that the TC here is higher, and we trust the TC from this approach more because the FRG is more exact than the RPA approximation. Because in RPA, you just do everything in one step, you do all the screening in one step. In the FRG, we sort of really gradually integrate out everything starting from the high energies. So that's the end of my talk. Let me conclude. So I've presented you a Kohn-Luttinger mechanism for superconductivity, which really only needs repulsive interactions in Bernal bilayer graphene. So there's no phonons in this model. And it leads to a P-wave superconducting solution, which can be enhanced either by applying a Zeeman field or magnetic field or spin-orbit coupling. And there's an asymmetry if you dope towards or away from charge neutrality. This is just coming from the properties of the polarization function and is consistent with the experiments as well. So with that, let me thank you for your attention, and I'm happy to answer any other questions you might have.
Thank you, Glenn, for this excellent presentation. Yes, question.
I have two questions. First,
how to determine the U and V, error U and V parameters in your calculation. And secondly, you think about the F wave gap in this system.
Okay, so your first question was about the U and the V parameters.
Error U and V.
Right, so let me go back. Yeah, so yes, so the U is the interaction within a patch, the V is the interaction between the patches, and in the sort of most approximate calculation, we just say, well, the Coulomb interaction is roughly 1 over Q, and the Q between patches is some number that we can extract from the band structure, and the interaction between a patch, the Q within a patch is much smaller, and this is why U is much larger than V for the on-screen the Coulomb interaction, the Bayer Coulomb interaction before we do the screening. So it's just related to the momentum.
You do not consider the Wagner orbital of this band. You think about some in the DFT, some calculate the U and V values. Sometimes the constraint alpha are used to using your band Wagner orbital shape. In this case, you determine the Q value in DFT or parts.
We have the wave function for each patch. From the wave function, you can read out the.
So my question, wave function is just the exponential.
The wave function is like per psi of A atom per psi B atom, and you know the Coulomb interaction, the density. You can write down the density, and the density interaction gives you the Coulomb interaction. And in this form, we take into account the 1 near form.
Right. So this is the model for the band structure that we're using, and the way this where this comes from is essentially some Wagner orbitals on this hexagonal lattice, and you construct a tight binding model from these Wagner orbitals, and then you expand this model for small momenta, and that gives you this kind of continuum Hamiltonian that's valid for momenta close to the K points, which are the momenta that we're interested in. So this is where all the matrix elements and everything come from. They come from this 4x4 Hamiltonian, which is an approximation for small momenta to the correct tight binding model coming from all the Wagner orbitals and so on. Yeah. So this is some Hamiltonian that we took from this work that's cited here by Jung and McDonald from 2014, where they did this proper Wagner calculation.
So you think about the F wave superconductor is not the P wave, the high order superconductor.
Right. So when we look at the superconductivity, we take the 4-point vertex and we just diagonalize it and find all the eigenvectors. And we find that the leading eigenvector is this P wave solution here. We didn't actually look at the TCs of all the other higher order parameters. In principle, they're all there in our diagonalization. We have all the eigenvectors, and we can just see what's the TC of the different symmetry sectors. But we didn't do that. We find that the P wave solution, always dominates throughout the whole phase diagram. And this S wave solution is mostly this extended S wave solution is mostly the subleading, and I don't really know what the sort of subleading instability is. Yeah.
Yes, please.
It is well known that for D-wave superconductors, the Josephson effect helps to identify this D-wave variant. Are you planning to collaborate maybe with experimentalists to prove this D-wave variant in these materials? Or is it possible in principle here for these built bilayers? Could you comment on?
Right. So yes, there's been these proposals using the Josephson effect. Also, actually, in twisted bilayer graphene, this was also a proposal to do that there. To the best of my knowledge, no one has done experiments that show it's D wave and or P wave or S wave in either of these materials. Yeah, so far the only experiments that have really been done in this material are mostly just these kind of resistivity measurements, transport measurements, Fraunhofer diffraction as well. So I think there's probably people working on it, trying to do this Josephson effect. Yeah, so I don't know how difficult these experiments are to do. But I'm sure that if they're possible, these experimentalists are working very hard to make it possible, because yeah, there's been a lot of attention, especially on twisted bilayer graphene, and if something is possible, then I'm sure it will be done.
Yes, another question.
Is the interaction marginal?
Let's see. So the interaction we use is just the it's this gate screened Coulomb interaction in 2D. So in that sense, yeah, it's
Let's do the some kind of dimensional analysis, but you need like some time to do that.
Yeah, I'm just thinking about, because it's the Coulomb interaction, where have I got it? Yeah, it's this form here. So it's 1 over q at large distances, but then it's sort of gate screened. So there's a divergence in the Coulomb interaction as q goes to 0, but you want to cure this divergence, and therefore you impose this gate screening. That's this ds, which is the length between the sample and the screening. And so yeah, it's got this sort of gate screened Coulomb form. So yeah, I would have to think about whether it's marginal or relevant. And it might be a bit subtle, because it's got this sort of crossover where it crosses over from 1 over q to a constant as you change q. So it might sort of depend on what q you're interested in as well.
Kind of the range of the energy.
Yes.
I have another question. So, what kind of dispersion do you use for electron dispersion? Is it parabolic or linear?
For the dispersion, so yeah, we just use this is the Hamiltonian we use for the dispersion. So it's got this trigonal warping term, which creates these 3 different pockets. So that's kind of important to include. In the most naive model of Bernal bilayer graphene, you just have 2 perfectly parabolic bands, 2 perfect parabolas. But here we're working at very low energies, very small doping, very close to this band touching point. And we need to include more details of the band structure than just the parabolic bands. And that's why we have this trigonal warping term, which leads to these 3 pockets, and that's crucial. I think without that, you find either a much lower TC or no TC at all.
So you use the linear one in this model?
So we don't linearize about the Fermi surface. We really we take the full dispersion. for the FRG, because for the FRG we want to integrate out stuff at high energies, and there the bands are not. You can't just use the linear approximation. Whereas for the RPA actually was done indeed by using a linear approximation. For the RPA, we just took the Fermi surface and we just linearized it around the Fermi surface and used that to extract TC. So that's another approximation that we used when we did the RPA, which we don't need to use when we do the FRG. So that's another sense in which the RPA is more approximate than the FRG.
Oh, yes.
Excuse me, in low energy Hamiltonian, you had the delta prime. What is the delta prime in that Hamiltonian? In B1 and A2 sub columns, let's say. Delta prime.
Right. So the delta primed. So the D on the diagonal, the D is just the displacement field, which has opposite sign on the two layers, and the delta is some kind of potential that is higher on the B1 and A2 sites, and this is just coming from the microscopic model parameters. It's not related to the displacement field. It's just if you take the tight binding model and you expand it, you find this delta prime term. So we just take that value from some microscopic theory. But actually, we also neglected the delta primed at some point, and it didn't change the results. So the delta prime doesn't seem to be too important. The more important terms are the terms like V4, and V3, which are describing this trigonal warping. I think those are really the important ones in this Hamiltonian.
Do we have any further questions?
So, sorry, simple question. So this B is related to the electrostatic doping, something called, or how do you generate this D?
The D is exactly, it's just this electrostatic gating, which is sort of above and below the sample. We've got some gates, some metallic gates. And D is roughly proportional to the voltage between these gates. Actually, it's a bit more subtle than that, because there's some screening effects as well. And there's some papers where they actually tell you exactly how D depends on the voltage. But in a very naive, simple model, D is just proportional to the voltage. But there's some more accurate refinements that you have to do.
Okay, any other questions? Seems not. So then let us thank Glenn again. And with this, we conclude our seminar. Thank you all for joining.
We can chat later. Thank you.